All right. Well, so our main program tonight are some students from Thomas Jefferson Science and Technology Magnet Space Club, and they're going to talk to us about their CubeSat project, which I know everybody's really interested to hear. So, guys, we've got the room, but we've also got about 30 people on our Zoom channel too. So, give everybody a chance to ask questions when you get a chance. So, let me introduce their teacher, who is also a Vienna Wireless Society member, Ms. Kristen Kusko.
Hi, everybody. Thank you for coming out tonight. I'm Kristen Kusko. I'm the advisor at Thomas Jefferson High School for Science and Technology, also the robotics lab director. And for the past 7 years, we've been working on a CubeSat. These gentlemen beside me have been working on it for the past 18 months, right? About Viraj a little bit longer, perhaps. Yeah, maybe. And what it was is it was a grant from NASA, the NASA CSLI grant that allowed us to do this. And again, the CubeSat's out there right now, and we're trying to see whether or not we can get it to turn on and listen to us or talk to us. And it's not so much the mission that we were worried about as much as the experience building it. So these guys are here. This is Nicholas Makovnik and Viraj Bala. They're here to talk to you guys tonight about the CubeSat. Thank you.
Good evening, everybody. Thank you for having us out here today. Like mentioned, we are students from the TJ Space program, which is an organization at the Thomas Jefferson High School, a public school located in Alexandria. So our program does many things, such as high altitude balloon launches, NASA outreach missions that go to the moon, and NASA science missions. Today we'll be talking about our satellite, TJReverb, which we recently launched to space. Before we get into that, though, just a quick thanks to all the people who helped us. So thank you to Jin Kang from Maru Space, the TJ Partnership Fund, which helped fund our project, and our incredible lab director, Ms. Kusko. Okay, so now we're going to get into a high-level overview of the project. So a CubeSat is a standardized form factor which allows for cost-effective access to space. It's standardized, so as you can see on the screen, there are different sizes. 1U means that the CubeSat is a 10 centimeter by 10 centimeter by 10 centimeter cube. 2U is two 1U CubeSats put together. 3U is 3 1U, and so on. So what the standardization means is that the hardware and the electrical systems are generally standardized, and we can also put multiple CubeSats into a single deployer and launch them all at the same time. So now on to TJReverb, which is our project. It's the Thomas Jefferson Research and Educational Vehicle for the evaluation of radio broadcasts. And it's a 2U CubeSat built by students from Thomas Jefferson High School with the main goal of determining the viability of using the Iridium Radio and the Raspberry Pi flight computer on CubeSats. So as students, we selected all the components, designed the stack, and wrote the entire flight software from the ground up. And we had another major goal. The reason that we did it all on our own was we wanted to educate other students and develop this incredible program that we did in TJ Space, and that's what we've been doing for the last couple of years. TJReverb was launched on November 26 on the SpaceX 26 ISS resupply mission from the Kennedy Space Center and deployed from the ISS on December 29. And over here you can see a picture of TJReverb. So here's a 3D rendering of our satellite without any of the solar panels. The stack itself is completely custom and designed by students in our club. And the components, most of them were donated or bought from companies, with the exception of the Raspberry Pi interface board, which was designed by our students. In the rest of our presentation, we'll be going more in depth on the Iridium Radio and the Raspberry Pi flight computer. Okay, so Iridium is a satellite phone company that operates a constellation of communication satellites in low Earth orbit. TJReverb has an Iridium Radio modem with a satellite phone subscription to communicate with the ground station. Iridium handles all communications with their satellites and the ground, so that was very helpful for us because we didn't need our own hardware ground station, which is often difficult and expensive to operate. Instead, we just sent and received emails to the Iridium SBD service. And another thing about Iridium is that it has built-in functions such as signal strength, geolocation, date and time, and checksum. It also implements its own low-level handshaking protocol between the radio modem and the constellation and the ground, which removes the need for us to consider that part of the protocol design. So here's the Iridium protocol. On the left, you can see the flight computer and the 9602N, which are modems that are actual physical pieces of hardware on TJReverb. And to the right of those is the gateway, which is our Iridium ground station. So each transfer that you see here is duplex, meaning that there's one mobile originated message and one mobile terminated message for each data transfer. This program was really useful because it allows for asynchronous communication. Since messages can be stored in memory at any stage of the process, there doesn't need to be a continuous line of communication from the satellite to the ground, unlike traditional systems.
Now we're going to get into some of the benefits of the Iridium radio itself. So the first, most notable one is the hardware is extremely low cost. So most space-grade hardware will be in the range of tens of thousands of dollars, while the Iridium modem is $250. And in addition to that, you save money because you don't actually need a ground station. On top of that, it has low power draw. So it draws 0.1 watts idle and 2 watts while transmitting, while radios like the APRS might draw 1.5 watts continuously. And it also doesn't require the low-level protocol design. So as we mentioned, a lot of that is abstracted to the Iridium ground station and to the modem itself. And it also, so we chose Iridium rather than a different service because it has very good coverage. As you can see here in the diagram, Globalstar has a lot of dead zones there. So Iridium also does have some downsides, especially the low bandwidth and small packet size. Because of that abstraction, it's limited to smaller packets, and we can't actually control the low-level flow of data. And also, it does require a subscription data plan, which has data limits. And when you go past them, then you start getting overcharge charges, like we did. So for us, it's 5 cents per SPD mailbox check with no message on the other end. So the issue with that is, if our satellite is in space and querying the constellation and there's no message waiting for it, we still get charged for that check, unlike with other radios. And then we also start, as I mentioned, getting charged more per piece of data after we go over our subscriptions data limit. And then as Viraj touched on earlier, there are difficulties with the full duplex communication logic. So we have to be careful to not discard received messages while we're trying to transmit. So now some of the use cases of the Iridium. So it's very useful for low data rate missions like ours. If you had a camera on the satellite, for example, you would not want to use Iridium because of the packet, the cost of transmitting data and the limited packet sizes. And it's also good for new CubeSat programs where you get to avoid the upfront costs of setting up a ground station and the technical experience needed for that. And then for the same reason, it's good for short duration missions because you're going to be paying less in the long term. So now we're going to get into the other side of our CubeSat, which is the flight computer, so the Raspberry Pi. So the Raspberry Pi is a consumer off-the-shelf microcontroller that's often used for small DIY projects. And we use it as our primary flight computer. And most of the benefits that it provides are because it runs Raspbian Pi OS, which is a light version of Linux. So some of these benefits include, as I mentioned, it's significantly cheaper to purchase and operate. So as I mentioned previously, space-grade computers can run in the tens of thousands, while the Pi itself is around $10. And it's also easier to use because it's essentially a microcomputer. It's running Linux. And it allows for direct SSH access. So for example, when we were on the ground, we could directly tunnel into our flight computer and upload code instead of having to program it with a separate chip. And it was extremely easy to run Python on it because it was a computer as well. So we didn't need to use Circuit Python, which is a lot more limiting. So the benefits that we tried to explore with this project mostly were interfacing the Iridium and the Raspberry to capitalize on both of their benefits. We're going to go over our program right now. So as Raj mentioned, we implemented entirely custom flight software, and we heavily leveraged the abstraction that Python provides, including automatic error handling. So here we have a little flowchart of our abstraction, the flight software. So the benefits of Python as compared to a language like C++ is that it's extremely easy to use. There's a low barrier, and a lot of students come into the program with knowledge in Python, or if they don't, it's very quick to use and pick up. And it also has many high quality packages. So for example, we were able to utilize an I2C package that meant we didn't have to deal with all the low level implementations. And it also allows for dynamic execution. So for example, we have commands on our satellite that allow us to remotely execute commands that we send up. And that's thanks to the uncompiled nature of Python. So now getting into the low-level details of the interfacing. So our Iridium driver is written in Python as well, rather than C++, which a lot of teams opt for. And it checks for contact and records the geolocation of the Iridium whenever we receive. And it includes message buffers, which are able to hold received commands until our software is ready to process them. And it also includes data encoding protocols for encryption and for compatibility, or compression and compatibility. So the benefits of combining these two are that we get to capitalize on the price benefits of both, the expertise benefits of both, and it allows for faster development times of the project, a lot more simplicity, and lower cost missions. And then sort of as part of the outreach mission of TJReverb, one of the things we did was we completely open sourced our software. So it's available on GitHub with this QR code here. And also to connect to the community, we also included features like being able to receive jokes from the satellite or play ultimate tic-tac-toe or chess against the satellite. So again, the significance of this project is that it shows that there are lower cost alternatives for the flight computer and the radio, which are two of the most critical parts of the satellite. And we can combine the Raspberry Pi and Iridium to utilize both of their benefits and minimize the development barriers and time that we need.
So now more information on like the current and recent status of the project. So like Ms. Cusco mentioned, we've actually been working on this project for around 6 to 7 years. And in the last around year or so, we really ramped up to finish assembly of our satellite, which was finished in May of 2022. Shortly after the assembly, we did a vibration test at USNA, which was successful. And a couple of months later, we handed it off to NanoRacks in July. It launched on the CRS-26 SpaceX rocket to the ISS on November 26th. And then after a month of being on the ISS, it was deployed on December 29th. And currently, we're still 2 weeks later awaiting contact. So, like I said, we're still waiting to establish contact with Iridium and APRS. However, in the last couple of weeks, or the last 2 weeks, we've been crowdsourcing and reaching out to other people, a lot of people around the country to help us find any leads and get any more information. We have a couple of possible theories, except right now a lot of it is still speculation. So our APRS may have started digipeating the ISS. And we also think we have the certain location of the satellite, but we're still not 100% sure. In the future, we're still going to keep trying to transmit with Iridium and APRS and just hope for the best. But also a special thanks to all these people that helped us out, especially you all here at the Vienna Wireless Society. Thank you for helping us establish contact, also for certifying a lot of our students for the ham radio. And also the Raspberry Pi modem that we mentioned earlier was actually designed by students at TJ along with people at Vienna Wireless. So thank you.
The Iridium modem was developed by a guy who graduated from TJ and also happens to be one of your members. So, but he still works at NEL Research, but it's still cool.
At the point where the satellite was separated from the space station, was there a final check on the transmitter? In other words, could it be received back at the ISS at the point when it was departing?
When we deployed from the ISS, we had a 30-minute delay before transmitting to prevent interfering, especially with the deployed antenna with the APRS, to prevent interfering with the ISS. But there were no last-minute checks aboard the ISS. All of them were done on the ground.
When was the last check done?
So that was right before we finished assembly, so sometime in May.
So what was the planned mission of this in space? Mainly to prove the concept here of the Iridium, or is there any secondary type of mission for this satellite once it's up and communicating?
Yeah, so the overall mission was to test the viability of Iridium and RPi combined in space. But a specific goal that we did have, a specific operational mode, was to measure the signal strength variability of the Iridium in low Earth orbit at the ISS's altitude, which is about 300 kilometers. But it seems like we will not be getting to that point in the mission.
How often was it planned to have the CubeSat try to contact one of the Iridium gateways to see if there's any messages waiting? How frequent?
So it was originally planned to contact the Iridium constellation every 40 seconds to query for messages, and every 5 minutes in charging mode when it's trying to save power to charge back up.
Do we think it's doing that now, even if we're not hearing it, or do we know?
It's possible. We haven't contacted it. And it's also possible that it's just tumbling because from the deployment videos, it did seem like it was tumbling a lot. So that's another possibility. For the NanoRacks deployer, essentially these CubeSats are stacked up in they call it the P-pod. It's like a rail, little enclosure for the CubeSats, and they're essentially shot out of it like a cannon.
Yeah, also like mentioned earlier, because of the interfacing with these CubeSats, multiple were deployed at the same time. So here you can see some pictures that were taken shortly after deployment. You can see that there are multiple CubeSats that are really close to each other. Ours is circled in red, but yeah, multiple are deployed at the same time from that P-pod that Nicholas was talking about.
Thanks. Very interesting project. Well done, gentlemen. I think one of you mentioned that you had a couple of hypotheses as to why we can't hear it or why you can't hear it, but I'm not sure that I heard exactly what those hypotheses were. So could you explain what your thoughts are and maybe whether or not you think you'll have a recovery and ultimately be able to hear? But what do you think went wrong?
So there are a lot of different things that could have gone wrong, and it's hard to debug because we have no access to the satellite essentially right now. Some of the most probable scenarios would be broken solder joints. So when it enters the vacuum of space, because we never actually did a vac test, some of the solder joints could have broken. Another is just the flight software had some bugs in it. And then the theory that I mentioned earlier was that the CubeSat is passively stabilized with a magnet, but that still doesn't alleviate all of the tumble. So it could possibly be tumbling, which would make Iridium contact a lot more difficult. And yeah, there are a lot of different possibilities, and we just have no way of confirming any of them. And at this point, we're still optimistic, but after a week, we would have switched to the APRS, which is our backup radio, and it's less likely to get contact with APRS than Iridium.
So the APRS radio, as far as we know, was actually designed and built by Bob Bruniga, the father of APRS. So we're pretty sure that's a good radio. But if the electronics and the other things failed, then that could be a problem.
How many years are you supposed to be in orbit?
So NASA guaranteed us 180 days. It's supposed to deorbit on July 31st because of drag in low Earth orbit.
We got a question on Zoom. So the question is, can you cover kind of the power system? How's it powered? Solar batteries, this sort of thing, and then talk a little bit more about the stabilization. And then they want to know if there's any chance of actually seeing it visually.
So while watching the deployment video, I can start answering some of the questions. So the electrical power system on board the CubeSat, we had 4 solar panels, one on each of the larger sides. So that's 10 by 20 centimeters on each side. we had a 5-cell lithium-ion battery, and we had an electrical power system, which was space-grade hardware that we used to interface between the solar panels and the battery. It was an ISOSpace EPS electrical power system. So for the stabilization, we originally intended to use a magnetorquer to orient the satellite and detumble, but that was deemed infeasible for a high school CubeSat team. So we descoped that, and we instead added a passive magnet to stabilize, to somewhat stabilize the CubeSat. So a magnetorquer has perpendicular coils that we can push current through, and that essentially creates a magnetic field and allows you to adjust the angle of the CubeSat.
And how about, is there any opportunity to see it visually? We can actually see it.
It's the size of two tissue boxes stacked on top of one another, so not.
It's 10 by 20 by 10 centimeters.
This is a great project. I was wondering if you could talk about the logistics, but what happened after it was arrived at the ISS. I imagine the people who received it probably never saw it before. They must have had some instructions, and they must have had a requirement to somehow arm the system just prior to launch. Perhaps you could describe those protocols.
Actually, what happens after it left TJ?
So back in July, myself and two students went down to Houston to do something called integration. And what we did was we brought the satellite in a Pelican case through National Airport, carry-on luggage. That was a delight. If you've ever taken something like that through the airport terminal, that was fun. I left my iPad behind because they were busy picking apart my luggage, trying to find all the other electronic devices that I had. So once I got everything to Houston with the kids, what happened was we went to Webster, Texas, where NanoRacks has their integration facility. So we got to go into their clean room, and what they did was they took one last look at the satellite, they weighed it, they did a whole bunch of checks to make sure that the solar panels weren't disturbed or anything like that, and there wasn't any debris that was going to fall off of the CubeSat, and then they took it and put it into the deployer. So NanoRacks was our mission manager, and they kind of took us the whole way through the process of from development to integration to launch to deployment. In fact, we just finally had our last meeting with them last week, which was kind of happy and sad at the same time. That's Cole Winkler right there. He was kind of our contact for the past year and a half, and what you'll see on the table is what they're doing is called a fit check, where they took our satellite and put it into a model of the deployer that's used on the ISS to make sure that it slid appropriately, could go in and out without any hesitation or interruption. So once we went down to NanoRacks and we integrated it, the other satellite that was in our deployer was DanteSat from Italy. And then they boxed it up, locked it up, and kind of let it sit in Webster, Texas for a couple months. Then in early October, they brought it out to Kennedy and they attached it to the Dragon capsule, where they started loading up the cargo for that particular mission. And the flight didn't go off as scheduled, as it never does. So a couple weeks on the, thanks to hurricanes, thanks to Artemis, thanks to all kinds of interruptions, we finally got to fly on the 26th of November. Once it took about 17 hours to get to the International Space Station.
So is NanoRacks, they're just responsible for the frame. They didn't have anything to do with the mission, right? The actual payload, the payload?
They did, in the sense that they made sure that we crossed all our T's and dotted all our I's. So they were the ones who handled our safety data template. They were the ones who were kind of like our interface as far as making sure we were legal, making sure we weren't going to build something that would blow up on the space station, because that would be bad. And pretty much held our hand the whole way through, which was great. But we're going to show you the launch, because that was an exciting day. The one thing that was kind of unfortunate about this whole deal was it all happened throughout the holidays. So we weren't all together. Like, this was the Saturday after Thanksgiving. So the team couldn't be together to watch it. And then the deployment happened on the 29th of December. So we weren't all together to see it happen. That's the Dragon capsule as it's trying to dock with the space station. And it goes very, very, very slowly, as you can imagine. But that's the view from the Dragon as it's approaching the space station. When you see the green dot, that's the space station looking back at the Dragon. And I think it goes dark, actually. I don't think we actually get to see the contact. And then what happens after it docks with the space station is it takes about 2 days. They just let it sit there for 2 days to make sure that the pressures and all that stuff is balanced out. And then, unlike moving on Earth, they have to take 7,700 pounds of cargo off of the Dragon capsule, which isn't as bad whenever you're in space because it floats. So it's not so bad. Any other questions?
Way back at the beginning of my career, I worked for NASA Jet Propulsion Laboratory. And one of the programs I worked on was going to be a space-based missile tracker that went up in the shuttle. And what I recall is they wouldn't let us put anything up in space that wasn't space hardened. We had to get our CPUs run through a special process. I mean, nothing would they let us put up in there. So how is it that you get to put a Raspberry Pi, a $10 Raspberry Pi, and an Iridium land-based modem on a satellite that goes up and gets deployed from the ISS? How is it that you're able to do that, and what are the implications of the ground-based hardware up in space? Is that maybe another hint?
So just on the mission side, and less on the regulatory side here. So space grade hardware is one of the reasons it's so expensive is because it's been tested repeatedly on multiple missions and has history. So it is riskier to send stuff like the Raspberry Pi and the Iridium modem to space. And that could have been a source of broken solder joints there as well with the soldered Raspberry Pi board. But the money that it saves is probably more beneficial for starting teams. Especially because there's so many different things that could go wrong. It's most likely not going to be the hardware itself. And then on the regulatory side, I'll pass it off to Ms. Kusin.
We don't know. The answer is that if NanoRacks didn't like it, they would tell us no and they would kick it off. That's how it works for us. Or that's how it worked for us.
Did you do anything special to the Raspberry Pi hardware, or did you just take a Pi Zero and shove in a micro SD card and do that? I would imagine if I were doing it, I would want the storage hard soldered and not just plugged in a socket.
So if I'm not mistaken, we did hard solder the connection to the interface board rather than socketing it. But in terms of extra procedures, we got like it was supposed to be a space-hardened SD card, which would be less vulnerable to radiation. But aside from that, basically just cleaning the solder joints after to prevent outgassing in space. It was not much more than that.
I liked Roger's question about once the CubeSat was in the space station, from that moment to deployment, did they have to turn the switch on before it shot out, or what was the steps once it was on board?
So we did have one remove before flight inhibit that we removed before we put it in the P-pod, the CubeSat itself, which was the first step of arming. And after that, we only had a few switches which were pressed while it was in the deployer, which prevented power from going from the battery to the flight computer. And that was essentially the extent of the arming. So the astronauts on the ISS didn't do any extra steps there. It was all based on when contact was released with those switches.
So the switches are depressed, and
Yes.
there's no power, and then when it gets ejected, they pop out and power.
The switches are electronically inhibiting power from going to the flight computer, or from the EPS.
Got some more questions on Zoom. Are you going to try again? And then in the presentation, you mentioned every time that your bill every time checks the Iridium mailbox. Have you looked at the Iridium account to see if there are any new charges that may indicate it called in?
Yes, we have checked the Iridium mailbox. So to the question, are you going to try again? So we are currently hoping to start off a new 3U satellite project in which we would develop a standardized bus that would let us swap out new payloads and put student projects on board in the future, because we like the satellite part of it more than the payload part of it. But we're currently trying to get funding for that, which is pretty difficult.
Also, even if we weren't able to establish connection, it was still a great learning experience for all of us. So we take that as a win, and we're still going to keep doing that in the future, regardless of what the projects are.
All right. So knowing what you know now, what would you have done different?
Well, I worked on the flight software, and I would definitely say that we learned not to overcomplicate it. So we tried to make the flight software extremely fancy, built-in air handling, mode abstraction. Honestly, it's better to just have something that's much simpler. There's less room for error in it.
I guess on the hardware side of it, maybe just more testing, because when it's down on Earth and you have the opportunity to fix it, you'd rather it break there than in space when you can't do anything.
I think the other aspect is that we put all of our eggs in the Iridium basket. And I think what we would have done is probably had one team dedicated to Iridium and one dedicated to APRS, because APRS is at least that was the one that seems like it was trying to talk to us. So I think that that's probably something that we would have probably done is paid each of them due respect, as opposed to just putting all our eggs in one basket.
I managed incredibly large technology projects for most of my career. And what I have to tell you is you guys did an amazing job with this. My understanding from Ms. Cusco is you had very little help from outside in the design of the flight software, in the design of the payload, in the design of integrating everything else. So I think you did a remarkable job given the limitations that you were under. And if you get a chance to do it over again, I know you're going to set the stage for a very successful mission in the future. Thank you, guys. Congratulations on contact or no contact. Remember, space is hard, right? Space is really hard. The fact that you got as far as you got is remarkable. Take it as a win. And again, having managed big technical projects, some that succeeded and many that didn't, a lot of the learning comes from that after action report when you sit down and figure out, all right, what are we going to do now? How do we think about it?
Of the 8 CubeSats that went up, ours was the only one developed by a high school. 3 of them don't work and 5 of them do. So we're competing with colleges and corporations, and we kind of held our own. So,
all right. Thanks, everybody.